Hello, in this video I'm going to work through a few problems in geometry, and in previous videos I've explained that using technology can help you reduce the time spent on problems while also helping you to improve your accuracy, or at very least help you check your answers. And in the case of geometry, actually it's quite different, where just drawing things out, simple sketches, and going through the calculations by hand on paper is actually faster, in my opinion, or in my experience. Because when you are using programs like Geogebra and other AutoCAD or other graphical programs, then you have to be precise and enter in all the different values for the line segments. And of course, it'll help you come to that same correct answer. But really it is quite a bit faster to just do things on your own when it comes to geometry, working with polygons and triangles and other shapes. These are bounded. You're not working with sine waves and complex algebraic functions. So Tom's got a piece of property that's 140 by 160. He's got a house that's 35 by 80. He's got a driveway that's 30 by 20. And then all around that area, except for the house and the driveway, he's got some grass. And he wants to put fertilizer on the grass, and so he needs to know how many square feet of grass he has, so he can figure out how many bags of fertilizer he needs. And so what we're going to do to find the area of the yard is just take that 160 by 140, and we're going to subtract from that the area of the house, 80 by 35, and the area of the driveway, which is 30 by 20. And this is fairly straightforward. You got 19,000 square feet. Just all rectangles, length times height, length times height. The area of the big rectangle minus the area of the two small rectangles. And so then we can figure out if each bag of fertilizer covers 5,000 square feet, 19,000 divided by 5,000, 19,000 square feet divided by 5,000 square feet per bag is 3.8 bags, or we would say he needs to buy 4 bags in order to cover the whole area. And finally, the fertilizer costs $18 per bag, and he's got 4 bags, and so that equals $72. And so that whole problem was relatively quick, whereas it took me 5 or so minutes to put this into GeoGebra, and came up with the correct answer there for the area. Of course, the GeoGebra did not help me with the other two. And we have to multiply this by a factor of 100 because I've scaled it down 1 to 10 on the x and y axis, and so we've got to add 10 times 10 again, or 19,000 square feet for the yard. So moving along, the next example took me even longer to graph on GeoGebra because there were more points and there were more particular angles. And so what we've got is just a conventional geometry problem where we've got some sort of shape and we need to find the areas within that shape. And so what we can do here is start by saying that the area, what we're looking for is the area of EAFD. The area of EAFD is equal to the area of AFD plus the area of EAD. So we'll split this up into 2 triangles. We've got this equilateral triangle here. We know this is an equilateral trapezoid, so we know that these 2 angles are equal at the top and the 2 angles at the bottom are equal, and we know that our side length here is 5, so we know this other side length is 5. If we know that this is an equilateral triangle, then all 3 of these sides are the same. That means that if this is 12, this is 12, and this is 12. And so then if we've got an angle measure of 60 degrees up here, 2 other angle measures of 60 degrees here, that means this angle measure is 60 degrees because in an isosceles trapezoid, we're going to have 2 parallel lines here. These 2 lines are parallel, and so our base angles here are the same as these angles here. And so then we know that this AD equals 17. And so in order to work with this top triangle, we're going to split this up into two triangles here. We got 30, 60, 90 triangle. We know this length is 16. What we can say is AE squared is equal to 16 squared. Oops, sorry. AE squared plus 16 squared is equal to AV squared, for using our Pythagorean theorem there. And so then we can find AE is equal to the square root of 33. And moving along, we can call this altitude. We can drop a point there, call that G. We're going to say FG squared is, FG squared plus 8.5 squared. So we've got the leg here. We're working with this right triangle, FGD. And so we're going to use the Pythagorean theorem again. FG squared plus GD squared, or 8.5 squared, is equal to 17 squared. And so we get FG then is the height of triangle AFD, and that's equal to 14.722. And so now we can find the area of that triangle AFD. Now we know the height already is equal to FG, and so we don't have to since we're working with the equilateral triangle, our height here is also our altitude, so we can say AFD is equal to 2 times AFG, right? 2 times the area of this here. And so we've got two of these right triangles, and so we can just drop that 1/2. 2 times 1/2 FG times AG. Right, we know the AG and GD are equal, and so the area of AFD is just equal to that altitude height there, 14.722 times 17, or 125.14. And then our area of ADE is equal to 1/2 times 16 times the square root of 33. And if you wanted to imagine that this is a triangle, or sorry, a rectangle here, then our area of a rectangle is equal to the length times the width. And then the triangle there, it just cuts these two angles here. And so our triangle on this side is equal to the triangle on this side. And that's where we get our triangle area formula there, 1/2 base times height, and this is equal to 45.96. And so we're going to add these two together, and we get the total area is equal to 171.1. So that's part A. Part B is pretty simple. We've got side length here is 17, side length 17. 17 plus 17 is 34, plus 16, we got 17 plus 17 plus 16 is 50, plus root 33, all equal to 50, plus the square root of 33. And so, like I said, it took me several minutes to map this out on Geogebra. And then we got the area there, 171.1. And if we wanted to, again, calculate the perimeter for part B, it tells us here, as we knew already, that the side length is 17, plus 17 is 34, plus 16 is 50, plus the square root of 33, which is 5.74. And you guys can use your calculators to do those decimals here. Finding square roots by hand is really one of those things that's best suited for a calculator, because you could spend quite a while trying to triangulate values. Moving right along, This next problem is just another standard geometry problem where we've got a circle, and then inscribed inside that circle we've got a bunch of different shapes. And so we're working to find an area. And in order to find that area, what I've done is labeled some other points in this figure. I've labeled this point D, and then I've labeled this point over here E, and this point F. And so in order to find our shaded area, we'll call that ABC, or ACD, the area of ACD. That is equal to the area of this larger triangle ABC, area ABC, minus the area of this this kind of odd shape of one square plus two triangles, which I call A, B, C, or A, B, C, D. All right, A, B, C, D. And so we can just go to solving for this diameter here, which is the hypotenuse of a right triangle. We know that it's a right angle there. Right, we know this is a right angle here. This is a square with equal side lengths. We know that this is a right angle. We know that this is a right angle because we've got two supplementary angles. We know that this is a right angle and this is a right angle because we've got a chord here which makes a right angle with this other chord, and then that's bisected, or that's divided by a segment coming off of this point here, which is at a right angle with the similar, or the equal segment coming off of that segment. Anyway, we've got a square and two right triangles. And so in order to find that diameter there, we're going to say AC squared is equal to 12 squared plus 11 squared. And so we get AC is equal to 16.279. Then the area of ABC is equal to 1/2 times 12 times 11, or 66. And we can just go right to solving for these values here. We know that this is 4, we know that this is 4. We've got right angles, and so we can find the areas of those triangles relatively easily. We've got the area of AED. AED is equal to 1/2 times 8 times 4, or 16. We've got the area of EDFB, that square there is just equal to side squared, or 16. We've got the area of that last triangle, DFC, is equal to 7 times 4 over 2, or 1/2 base times height, and that's equal to 14. We're going to add all these up, and we get 46. And so then ACD is equal to 66 minus 46, or 20. And that was relatively painless, pretty simple. Of course, it looks a lot better on Geogebra, but it took several minutes to get all these points plotted out properly, and then we get our area there of 20. So the main benefit of using the graphing utility is that it's to scale. All of the angles are correctly measured. We've got the graph line paper on the background. You've got all of your points plotted out here. And it just looks a lot better than my scribbles, but it does take quite a bit more time. In this last example, I'm going to work through the hand calculations and then use Geogebra to check it. All right, so we've got a semicircular driveway here, Sue and Dave. Their names really don't matter. We've got a semicircular driveway. And so semicircular means that there would be the other half of the circle here and the other half of the circle here, and that's going to help us find the area of the actual driveway itself. If we've got a 12-foot driveway across, that means we've got another radius of 18 feet here. And so we can just go directly to solving the area of the big circle, which is the outside perimeter, the outside circumference there. is equal to pi r squared, or pi times 30 squared, which is 2827.433. The area of the small circle is equal to pi times 30 minus the driveway, or that's 18 squared, which is 1017.876. And so the area of the drive then is just the area of the big circle minus the area of the small circle, divided by 2 because we only have half a circle. We've got semicircles, and so that's 904.779 square feet. And you can say this is about 905 square feet if you want. So that's part A. What's the number of square feet to be resealed? Part B, if Dave can reseal the driveway at a cost, again this is just simple algebra for cost, which Geogebra will not help us with. Cost is 45 cents per square foot, 0.45 times 904.779 is equal to $407.15. If you estimated 45 cents rounded to 905 square feet, that's going to give you, I believe, 407.25 there. Close enough. And C, if individual flowers are to be planted 1 foot from the edge of the driveway in intervals of approximately 1 foot on both sides of the driveway, how many flowers are needed? So we're going to increase the radius here. We're going to plant flowers 1 foot, 1 foot. We're going to decrease the radius here on the inside, plant flowers 1 foot from the driveway at 1 foot intervals. And so then we're looking for circumference. Our circumference of the outer circle, the outer edge of the driveway, is equal to 2 pi r. Remember, it's r plus 1, but we're going to divide by 2 because we've only got a semicircle there. And so that's equal to 31 pi, or 97.39 feet. And the circumference of the inner circle is equal to the inner semicircle, pi times r minus 1. Which is equal to 17 pi, or 53.41 feet. And then, so we add these two together, and we get 97.39 plus 53.41 is 150.79. Now that's feet, and so we're going to say this is equal to 151 flowers. Right, so that's our part C. Now, in order to put this into GeoGebra, we need to start with a circle. We're going to say circle with a center and radius. So we'll start at here, radius of 30. You have to zoom out. All right, then we're going to have to put in, should have said another semicircle. Let's put a couple points on that circle and on the grid. And then we can see if we can erase that. Nope. Let's put some points down first. So we got 1 point at 30, 1 point at negative 30. And then we're going to draw a semicircle through those 2 points. There we go. And then we're going to put down another point at, I have to change that to negative 18. And then another one here at 18. Lay down another semicircle. And then we can put a couple line segments to make the edges of our driveway there. D should not be there. It should still be at negative 18. All right. And so what we're looking for in part A is to find the number of square feet to be resealed. Oddly enough, I believe that in this example, our GeoGebra is going to be slightly faster. Area of points. We're just going to work from C, B, E, D. Area equals 0. That makes no sense. Oh, because it's on, half of it's on the right side of the y-axis and half of it's on the left. All right, so let's start again. And so then that little part of GeoGebra has actually made it so yes, in fact, it's faster. All right, so if we've got a radius of 30, that means we've got a diameter of 60, and we'll put this one here, 18, 0, and then another one at 36, 0. No, these should be 12. That should be a 12. And this one should be 12 from 60, which is 48. Draw our semicircles. Line segments. And let's try to find the area again. The area of A, B, D, C, still 0. Well, that's pretty odd. And so I think this is illustrating my point relatively well, that it's not too easy to find the areas on GeoGebra as compared to just doing it by hand. A, B, D, C? No. The area of AB? No. Well, that's not fun. The area of C. Okay. But that is, well, at any rate, this is the correct answer. And so I think I illustrated my point fairly clearly that working with geometry in GeoGebra, oddly enough, is not so convenient, whereas if you just have a notepad and you know some basic techniques in arithmetic and the quick formulas, that is really a lot faster than trying to draw all of this out on some sort of CAD program and find your areas that way. But when it comes to algebra, and especially calculus and working with sine functions and relative extrema and minima maxima, this type of thing, it's much faster to use a graphing program than it is to do it all by hand. So sometimes we win, sometimes we lose with technology, or sometimes technology wins, sometimes technology loses. Today I think GeoGebra lost to old-fashioned techniques. Okay, thank you.